Our project is on the fluid mechanics of the DARPA Falcon Hypersonic Technology Vehicle 2. The Falcon HTV2 is a joint project between the Defense Advanced Research Project Agency, also known as DARPA, and the United States Air Force. It is part of the military's Prompt Global Strike effort and is capable of speeds up to Mach 20. The HTV-2 is designed to be launched into space by a Minotaur 4 light rocket, disengage from the rocket, re-enter Earth's upper atmosphere, and fly to its destination. The first test flight was conducted on the 22nd of April, 2010, and the second test flight was conducted on the 11th of August, 2011. Both test flights ended prematurely with the HTV-2 crashing into the Pacific Ocean. My name is Albert Nguyen, and my research question is, what is the drag force that is applied to the Hypersonic Technology Vehicle 2 after it has re-entered Earth's atmosphere and is in its gliding phase? My hypothesis is that the drag force applied to the HTV-2 should not be very high compared to other aircrafts due to the fact that the HTV-2 is much smaller in size and is flown higher up in the atmosphere than normal aircrafts. With the data gathered about the HTV-2, we calculated the Reynolds number to be 1.68 times 10 to the 9th, meaning that the airflow about the aircraft is turbulent. Using that information, we find that the drag coefficient is about 0.0015. The drag force that we were able to calculate for the HTV-2 was 45.90 pounds force. This calculation proves my hypothesis correct, with the HTV-2's drag force being much lower than other conventional aircrafts, such as the Lockheed F117 Nighthawk, which has a drag force of 528.17 pound force.
So the question I came up with was, how was the Hypersonic Technology Vehicle 2 affected by the boundary layer during the flight? And my hypothesis was that the HTV-2 failed due to the boundary layer getting larger at higher Mach speeds. So the importance of the boundary layer is that it allows air to change its velocity from the upstream value to 0 on the surface body, and at hypersonic speeds, the boundary layer thickness thickens and becomes more resistant to disturbances. And the definition of the boundary layer thickness is the distance across a boundary layer from the wall to a point where the flow velocity has essentially reached the free stream velocity. And how I got the boundary layer thickness is that I used a semi-empirical boundary layer thickness equation, and I've shown this equation. Here, gamma represents the specific heat ratio, which is 1.4 for air, and the TW over T naught, it's assumed to be 1 as in adiabatic wall condition. The TW represents temperature of the surface or the wall of the HTV-2, and T naught represents stagnation temperature. The M with subscript infinity represents the Mach number, which was 20, and the CW is the Chapman-Roussian coefficient, which is given through an equation, and that's divided by the Reynolds number and multiplied by X, which is the length of the HTV-2 vehicle. And after I plugged in all the numbers, and the equations is given through the report, it came out to be 0.327 feet. And here it just shows that as the Mach number increased, so did the boundary layer thickness, and from 0 to 20, the Mach number 0 to 20, the boundary layer did increase, proving my hypothesis to be correct. Thank you.
Hello, my name is Jimmy. I'll be introducing the next research question. Did the misinformation of the Pitot tube cause the pilot to crash the aircraft? If the Pitot tube, which indicates the reading of the aircraft's velocity, malfunctions, it may cause the pilot to incorrectly navigate the aircraft, leading to a program execution, causing the aircraft to purposely crash. Pitot tube measures the velocity of an object by analyzing the pressure of the air. Problems occur when readings misinform the pilot. An aircraft with an understating velocity reading may trick the pilot to accelerate, which can result in the aircraft breaking apart at higher speeds. On the other hand, an aircraft with an overstating velocity reading may trick the pilot to decelerate, resulting in engine stall. Here we have is an airplane pitot static probe. The above picture is a schematic. The bottom is an actual photograph. Here we have a pitot static tube. Using Bernoulli's equation, we developed a final equation where the actual velocity equals the square root of 3000 squared divided by x, where x is the actual reading. Here is a graph displaying the aircraft's actual speed with respect to reading accuracy. As you can see, as the speed indicator is increasingly damaged, the actual speed of the aircraft increases exponentially.
Hello, my name is Hao-Yi Kung, and then I will be doing the following research question, which will be is the drag force larger than the launch due to altitude? Although the rocket launcher, it brings up the aircraft to the atmosphere. My hypothesis will be the drag force for the rocket launcher will be much higher than the drag force of the HTV, which will be the aircraft, although it released the HTV into the space. This slide will be showing the numbers I get for the HIIB, the rocket launcher, and there will be the numbers I calculated for the Reynolds number, coefficient drag, and drag force. For the analysis, according to the result from Albert's analysis from question 1, compare the drag force between the rocket launcher and the aircraft, which will be nearly 6 times 10 to the power of 8 pounds force over only 45.9 pound force, which shows a large difference in between. This calculated result will show the altitude and the velocity vary the drag force. In this case, the drag force is the resistance experienced by the rocket launcher. So when the altitude increases, the air becomes thinner and attributes to less drag force on the rocket, and eventually gives a pretty small drag force to the HTV, which will be the aircraft being released into the space. Furthermore, for the lifting forces, there should always be the lifting forces present for the flying vehicles, but in this case, the rocket flies vertically into the sky, which is impossible for it to grab the air by wings.
So in conclusion, the Falcon project was a government project to develop a rapid strike hypersonic weapon system, and the specifications of the design of the HTV2 are disclosed to the public, as well as the main reason why it failed. But our own analysis of the drag lift, boundary layer, rocket launcher, and the Pitot-2 helps us form our own hypothesis concerning the HTV2. For the drag force of the HTV2, compared to a F-117 drag force, it was a lot smaller, being 45.9 pound force, and this is due to the smaller surface area of the drag force on the HTV2. As for the rocket launcher, it was much larger, of course, compared to the HTV2, since the rocket had to travel from ground past space, which had a lot of wind resistance, and also the air is thinner at high altitude, so that the HTV2 had thinner air to travel through compared to the launch of the rocket. The boundary layer thickness of the HTV2 was 0.327 feet, and also proven that as the Mach number increased, so did the thickness. And for the Pitot-2, we found a correlation between the accuracy reading to the speed that the HTV2 will have to travel. So say if the reading accuracy is just off 10%, the vehicle would have traveled more than 700 miles per hour, more than anticipated. And this is our main hypothesis of why it failed was due to the programming of HTV2, because if it detected any problem or any unsafe occurrences that may have came up, then it would automatically crash into the water. But we don't know what came up, what was the problem. So it may have been that the boundary layer was too thick and then may have caused instability, or that the heat at high speeds may have been too much for tolerance for the vehicle. So the problem we couldn't, or just because that this is such a secretive project, the main reason the failure wasn't released. So we can only speculate with the knowledge given whether our hypothesis of why it crashed are accurate or not. Thank you.